Pretty much everything in our modern world is built on a foundation of software. I mean, the apps in your pocket, the airplanes in the sky, the entire financial market, it's all code. But what happens when that foundation cracks? When just one tiny mistake in one line of code slips through? Well, the consequences can be absolutely catastrophic.
So, to really get why measuring software quality is so critical, we've got to look at a time it went spectacularly wrong. This is the story of one of the most expensive and literally explosive software failures in history.
$400 million! Let that sink in. That's not the price tag for a whole space program. Nope. That was the cost of a single rocket and its payload, completely vaporized in an instant, all because of one little software bug. So here's the story. It's June 4th, 1996, and it's the first ever flight of the Ariane 5 rocket. And for about 36 seconds, everything is perfect. But here's the problem. The engineers had reused a piece of the guidance software from the older, slower Ariane 4 rocket. The new rocket, Ariane 5, was way faster. And right around 37 seconds into the flight, a number representing the rocket's velocity, a big 64-bit number, tried to cram itself into a tiny little 16-bit space in the software. It's like trying to pour a gallon of water into a coffee cup. It just overflowed. The primary guidance computer crashed. And then, get this, the backup computer, which was running the exact same software, failed for the exact same reason. The rocket went haywire, veered completely off course, and just 40 seconds after liftoff, it blew itself up.
Think about that. All of that destruction, all that money, gone. And it all came down to one tiny data conversion error. This disaster forced the entire industry to ask a really hard question. How on earth do we build these unbelievably complex systems and stop this from ever happening again?
Well, the answer is about making a shift. It's about moving software development away from being this unpredictable art form and turning it into a real, rigorous engineering discipline. And what's the bedrock of any kind of engineering? It's measurement.
I mean, think about the old days of software, the craft era. It was basically chaos. You'd ask a developer, hey, when's this going to be finished? And you'd get a shrug and an answer like, when it's done. But once we started measuring things, like a team's velocity or the density of bugs in the code, we could suddenly give real answers. We can make estimates, we can project costs, and we can actually define what good enough means with real numbers. Measurement is what turns that chaos into predictable engineering. And this isn't some new idea. The physicist Lord Kelvin said it perfectly a long, long time ago. To measure is to know. If you cannot measure it, you cannot improve it. That's it. That's the whole philosophy right there. If you can't put a number on the quality of your software, you're just guessing. You have no systematic way to actually make it better.
Okay, so we're all on board. We need to measure. But what are we even measuring? I mean, how do you take something as fuzzy and abstract as software quality and slap a number on it?
Well, the first thing you have to realize is that quality isn't just one big thing. Smart people have created frameworks like this one, ISO 9126, that break it down. So instead of one vague idea, we have these different characteristics. Functionality is basically, does it do what we said it would do? Reliability is, does it keep doing it without crashing? And we can get even more specific. Is it easy to use? Does it hog your computer's memory? Can we fix it a year from now without pulling all our hair out? Each of these pieces can be measured.
And this is how we connect those ideas to actual concrete numbers from the code. Let's take that maintainability idea. How do we measure that? Well, we can use something called cyclomatic complexity. It sounds fancy, but all it really does is count the number of possible paths through your code. So every if statement, every loop, every decision point, just think of it like a roadmap. The more forks in the road, the more complex it is. And more complexity usually means it's harder to understand, harder to test, and probably has more bugs hiding in it. These tools take that gut feeling a developer has about messy code and turn it into a hard number you can actually track over time.
But hey, measuring the code itself, that's really only half the story. We can also measure things from the user's point of view using something called function points. Now, instead of counting lines of code, which, let's be honest, your users couldn't care less about, this method counts the actual features they can see and touch. How many input screens are there? How many reports can they generate? How many queries can they run? This is so powerful because it completely shifts the focus. You stop measuring technical effort and you start measuring the actual value you're delivering.
So this is great, right? Problem solved. We'll just measure everything and we're going to build perfect software from now on. Easy. Well, not so fast. Unfortunately, it is not that simple.
This is where the story takes a really interesting twist, because the act of measuring something can create a whole new world of problems all by itself.
And this brings us to a concept that you absolutely have to understand, called Goodhart's law. It's so important. It says, when a measure becomes a target, it ceases to be a good measure. What does that mean? It means the second you tell people that their bonus or their job or their performance review depends on hitting a specific number, they'll stop caring about the goal the number was supposed to represent, and they'll focus only on making that number go up, no matter what.
For a perfect and kind of devastating example of this, just look at the Wells Fargo scandal a few years back. The metric they used was super simple. How many new bank accounts does an employee open? Step 2, the incentive. You get a bonus if you hit your target. And the results? It was a disaster. Employees opened millions of fake, unauthorized accounts just to hit their numbers and get their bonuses. See, they hit the target, but they completely destroyed the actual goal, which was to get more real customers.
Okay, that's a wild story from the world of banking. But how does this kind of thing, these weird incentives, show up in our world, in software development?
Oh, believe me, it happens all the time. Imagine a manager says, "We're going to reward developers based on how many bugs they fix." What happens? Well, some sneaky developer might just be tempted to write a bunch of simple new bugs on Monday just so they can fix them on Tuesday and look like a hero. Or here's a classic one you see everywhere. Management mandates 100% test coverage before you can merge your code. So what do you get? You get developers writing tons of useless tests that don't actually check for anything important, but they do make the coverage number go up to 100%. The target is met, but the quality of the software is no better. In fact, it might even be worse.
This is what's known as the coverage paradox. It turns out that the thing that actually finds bugs isn't the final percentage number. It's the act of writing a wide variety of really thoughtful tests. A high coverage number is often just a side effect of good testing. It's not the cause of it. The moment we make that side effect the main goal, the whole system just falls apart. So if targeting metrics is so dangerous, what are we supposed to do? Should we just give up and go back to the when it's done days? No, absolutely not. The answer isn't to stop measuring. The answer is to get a whole lot smarter about what we measure and, even more importantly, how we use those numbers.
And here's a perfect example of a trap, relying on a single number, like an average. So you look at your dashboard, and it says your app's average response time is 500 milliseconds, and you think, awesome, we're fast. But that average could be hiding a terrible secret. It could be that 95% of your users are getting a super fast 200 millisecond response, but that last 1% are stuck waiting 30 full seconds for the page to load. For them, your app is totally broken, and they're probably never coming back. Averages can lie. You have to look deeper.
You know, the best way to think about a metric is this. A metric is not the truth. A metric is a flashlight. Imagine you're in a big, dark, complex room. A flashlight is an amazing tool, right? It shines a really bright light on one specific part of that room. But it doesn't show you the whole room. It's a tool for investigation, not the final answer. To really understand what's going on, you need a bunch of different flashlights, all pointed at different parts of the room.
And that brings us to the final, and I think the most important, question you have to ask yourself about your own work. All those engineering metrics, your bug counts, your test coverage, your performance numbers, they're really good at measuring your outputs. They tell you how well you are building the thing. But do they measure the outcome? Do they tell you if you're building the right thing? Are your users actually more successful because of your work? Is the business growing? That is the crucial difference. So don't just measure the code you write. Measure the impact that code has on the world. Because that's how you measure what truly matters.